Hello and good day. Today we are going to be learning about exponential functions, and even though the name might seem pretty scary, we're not going to get too crazy with them. Just want to give you guys a little bit of an introduction to them. An exponential function by definition has this form: y equals a times b to the x. Sometimes it is helpful to put the b to the x in parentheses so that you can be reminded of PEMDAS. PEMDAS, you remember, is parentheses first, exponents, multiplication, division, addition, and subtraction. So a lot of times people try to multiply a times b first, but actually exponents are, the e comes before the m. So you want to do the exponent first and then multiply the result. And again, we will talk about that as the lesson continues. A couple of things that I want to be clear here. For an exponential function, the a, this value here, is not 0, and that should make sense. An exponential function is a function where the variable is in the exponent, so you can see that the variable up here is the exponent. Some examples here, we've got y equals 0.5 times 2 to the x. So obviously when you look at this expression, there's lots of variables, so when I say that the exponent is a variable, you're like, oh, well, aren't they all variables? Well, yes, but when you look at it in this case, you have, a is a number, b is a number, and then x is the variable, and x is the exponent. And that's what we call them exponential functions. And again, you will recall what I said earlier, a lot of times students try to go 0.5 times 2 and then raise it to the x power. But no, you go 2 to the x power, and then whatever you get from that, you multiply by 0.5. Another example of an exponential function is negative 2 times 0.5 to the x power. I put these functions up here because I wanted to kind of show you where we've been. We've done linear functions like y equals 3x minus 5, and in this case the variable is not in the exponent. If anything, the exponent of the variable is 1. And then you have the parabola here. We have y equals 5x squared. Again, the variable is not the exponent. The 2 is the exponent. So just a couple of examples of what we've done in the past and how this is now different, being that the variable is now in the exponent. So if we allow a to be 0, well, 0 times anything is 0, and so all you would have is y equals 0, and that wouldn't have an exponent or it wouldn't have a variable in the exponent. So that's why we say that a cannot be 0. Also, b has to be greater than 0. So this number here, the b, has to be bigger than 0. So positive, basically. So you can see that here b is 2, and here b is 0.5. Both of those numbers are positive. Notice that the a value doesn't have to be positive. In this case, a is negative, but the b value has to be positive. Also, it can't equal 1. Now, it can be something bigger than 1, but it just can't equal 1. It can be smaller than 1 as long as it's bigger than 0, but it can't actually equal 1. And again, the reason for that is because if we allowed b to be 1, then you could have something like y equals 1 to the x power, and we know that 1 to any power is 1, so then the equation would just be y equals 1. And like the case of y equals 0, this is not exponential because there's no variable in the exponent. So again, just a couple things to remember. A is not 0. B has to be bigger than 0, not equal to 1. But like I said, B can be bigger than 1. It can be 2. It can be smaller than 1. It can be 0.5. Okay, so for our examples today then, we're going to be dealing with exponential functions. The first thing we want to learn how to do is how to evaluate exponential functions. And you evaluate an exponential function paying very close attention to PEMDAS. Okay, so we're going to start here with this first example. Excuse me, I'm losing my A there. And the example says y equals 5 to the x power. And there are two different ways that they will tell you how to evaluate a function. One is they'll actually just tell you what the x values are. They'll say for x equals 2, 3, and 4. So I need to evaluate this function 3 times for 3 separate numbers. Another way that they'll do that is they'll call it the domain. Domain is the input. So in this case, instead of saying that x equals negative 3 and 6, they've given me the domain, and the two numbers that are in the domain are the two x values that I need to evaluate. So for y equals 5 to the x, I am going to first evaluate for x equals 2. So I'm going to go y equals 5 to the second power, which we know is 25. So that's my first answer. When x is 2, y is 25. In my second example, I get 5 to the third power. And now that's going to be 5 times 5 is 25, and 25 times 5 is 125. So when x is 3, y is 125. And then lastly, y equals 5 to the 4th power. Okay? And so that's going to be 5 times 5 is 25. 25 times 5 is 125. And then 125 times 5 is 625. And you can use a calculator if you must. But basically when x equals 4, y equals 625. One of the things that you'll notice about these functions is that they get big very fast. When x is 2, y is 25. And when x is 3, it jumps all the way to 125. That's a huge jump. And then from 125, it jumps all the way to 625. So basically things get really big really fast with exponential functions, or they can get really small really fast if they're negative. So now we're going to go to t of n, and this is a different notation, but basically we're being told that n is the variable here, n is the exponent there, and these are n values. In the other case they were x values because the variable of choice was x in that equation, but in this one it's n, so we just threw it the same way, but I'm actually looking for t of -3, and you remember that in the last lesson we had something with n's in them, we had those geometric sequences, so it's kind of the same thing, you're plugging in -3 for the n. So this time we have 4 times 3 to the -3 power. And I want to remind you, in A, there was no number in front of the b to the x part. In this case, you have a and b to the x. So again, I want to caution you that you don't go 4 times 3 is 12, or 4 times 3 is 12, and then 12 to the -3 power. You deal with the exponent first as per PEMDAS. Okay, exponents second. Okay, there's no parentheses here, so the first thing I would want to do is use my properties of exponents to put my fraction bar. The 4 does not have a negative exponent. The -3 is not attached to the 4, it's only attached to the 3. So the 4 will stay on top, and then the 3 to the -3 power will move to the bottom as a +3. And then I can simplify my answer by saying 3 times 3 is 9, and 9 times 3 is 27. So at the end of the day, I get 4 over 27. So again, when n is -3, the t of n value is 4 over 27. Okay, and then we have a 6, so we're going to go ahead and do this again for 6. This time we're going to be putting in a 6 in the exponent. All right, but again, we don't go 4 times 3 is 12. We go 3 to the 6th power, and I'll get my calculator for that, it's a little bit big. So 3 to the 6th power is apparently 729. There's no negative exponent this time, so I don't have to move anything to the bottom, but it's 4 times 3 to the 6th power, which is 729, and then 4 times 729 is 2,916. So when n is 6, the value of this function is 2,916. All right, so now we're going to have you evaluate 1, 2, and 3. There's one like part A, and then these two functions are a little bit more like the part B that I did earlier. And of course it says for the domain, so -2, 0, and 3. So you're going to be evaluating each function for those 3 values. All right, cool. So then in our next part of our lesson, what do exponential functions look like? We know that linear functions look like lines, and that parabolas, have a U shape, that absolute values have a V shape. Well, this is what an exponential function looks like. And by the way, these are 4 separate functions, so they're 4 separate graphs. I put over here that b is greater than 1. So these 2 graphs are showing you examples where the b value, which is 3 over 2, which is 1.5. So this is bigger than 1, bigger than 1. And in this case, 2/3 is not quite 1, it's 0.66666. So 2/3 and 2/3. So these values of b is smaller than 1, but it's bigger than 0, because remember we said earlier that it has to be bigger than 0. So I just wanted to show you what these graphs look like. And like we said earlier, the exponential functions start off increasing at a very slow rate, and then they just shoot off. As we saw with that whole 25, 125, and then 625 situation earlier. So I just wanted to give you an idea of what's happening with these graphs. These graphs are pretty much the exact same graph. This is y equals 3/2 to the x power. This is y equals -3/2 to the x power. So the negative is out in front of the parentheses. And you can see that what's happening with that negative is that when you have a positive exponential function, this is what it looks like. But when you have a negative in front, it basically flips the graph over and you have this blue graph here. We call that an x-axis reflection because it's like a mirror image, a reflection, and like when you look in the mirror, it's a reflection on the x-axis. So when you have a negative in front of an exponential function, as long as the b is bigger than 1, then it's going to have an x-axis reflection. Now this guy is what we call a y-axis reflection. When you look at the red graph from this side and the red graph from that side, it's basically flipped on the y-axis. So if you were to take this graph and flip it over there, then it would be basically this red graph. And if you were to take this blue graph and flip it on the y-axis, then it would look like this graph. All right? So these are y-axis reflections of that. But again, the reason why that's happening is because in this case, these two examples, as I said earlier, the b value is between 0 and 1. So it's smaller than 1 but bigger than 0. So when you have a b value that is smaller than 1, it's going to look like these graphs. If it's negative, it's going to flip over, like we said earlier. If your b value is larger than 1, like 1.5, 2, 4, 3, anything bigger than 1, it's going to look like these graphs here, primarily the red. If it's negative, it'll look like the blue. So I just want to give you guys an idea of what they look like. And so then we're going to be graphing some. So here's an example, and I'm going to be graphing this. And when you want to graph an exponential function, you always want to start with a t-table. And you want to be very careful that you always choose values that are both negative and positive. Don't just pick positive numbers. So I'm going to start with -2, -1, 0, 1, and 2. Not a bad place to start for my t-table. Now remember that when you do a t-table, you can choose the x values, the domain part, but you can't just choose the y values. To get the y values, you have to plug it into the equation and solve them. So basically you have to evaluate, like we were doing in the previous example. So what I'm going to do right now is I'm going to do that. I'm going to start evaluating here. Let's get a different color here. Okay, so we have y equals 3 times 2 to the -2 power. I'm going to evaluate for x is -2. So again, we use our properties of exponents, and the 3 stays on top because it doesn't have a negative exponent. The 2 to the -2 power will go to the bottom as a positive exponent, and then we get 3 over 4 because 2 squared is 4. So that means that when x is -2, y is 3/4. And then we do it again. Y equals 3 times 2 to the -1 power. Same thing, the 3 is not affected by the negative exponent, so it stays on top. And then 2 to the -1 power brings the 2 to the bottom with the positive exponent 2 to the 1, which is just 3/2. So when x is -1, y is 3/2. And then we have y equals 3 times 2 to the 0 power. And again, our properties of exponents say that anything to the 0 power is 1, so we get 3 times 1, which is 3. So when x is 0, y is 3. And then we're going to go y equals 3 times 2 to the 1 power. And that's 3 times 2, which is 6. So when x is 1, y is 6. And then lastly, we're going to get y equals 3 times 2 to the 2nd power, which is 3 times 4, which is 12. And we put our 12 right there. Okay? So again, notice that in all these examples, at no point in time do I go 3 times 2 is 6. That is not the first step. Exponents first, multiplication afterwards. So now what I need to do is actually graph this guy. I'm running out of space here, but hopefully we can. I'm going to get -1, -2, and then we're going to have 0, 1, 2. All right? So when x is -2, I'm going to go 2, 4, 6, 8, 10, 12. I'm going by 2's because I'm running out of space here. But when x is -2, y is 3/4. So this is 2. So 1 is right here. And 3/4 is not even 1 yet. So at -2, it's going to be roughly right about there. At -1, it's 3/2, and 3/2 is 1 1/2. So at -1, we're going to get a little bit higher up here. And then when x is 0, we're going to get 3, and that's going to be right in the middle of 2 and 4. So there's that guy. When x is 1, we're going to go to 6, so 2, 4, 6. And when x is 2, we're going to be all the way up at 12. So basically, you're going to get a graph that looks like that. And again, you can see how it starts off really small, increasing at a really small rate, and then it just starts getting really big. Okay, so that is your graph. And so now you can try these graphs on your own. Remember that you don't want to go 0.5 times 2. You want to evaluate this first and then multiply by 0.5. And again, you can choose your x values, but make sure that you have negatives, 0, and positive. And once you've done that, then you will have completed the lesson for today. Thank you, and thanks for watching.